Welcome to our quantum deep dive. Today, we're going deep into a particle that just might hold the keys to some of the biggest secrets in all of physics.
Absolutely. And, this whole deep dive is actually based on a brilliant essay by Yurgo Shinepet. We're going to be talking about a particle that's, well, it's a lot stranger than you might imagine. So let's just jump right in.
Okay, so just think about this for a second. What if there was one single, incredibly short-lived particle, something born out of just unimaginable energy? And what if that particle could somehow be the bridge between the very first moments of the universe and the most advanced technology we can dream up for the future?
It's a massive question, right? And like I said, the answer, well, it's going to get weird.
Right. And the particle at the very heart of this whole thing, it's called the Anti-Lambda baryon.
Yep, it's this really exotic little piece of antimatter. And over the next few minutes, we're going to break down what it is, where we even find it, and why it's suddenly becoming a huge deal for the future of science.
So here's how we're going to tackle this. First, we'll take a look at this idea of a particle from the mirror world of antimatter. Then we'll get into the baryon family tree to see where it fits.
After that, we'll get into the anatomy of the antilambda itself, and then see how these things are forged in what are basically star machines. From there, we'll explore the quantum frontier and finally ask that huge question: what could an antimatter future even look like?
All right, first up, a particle from the mirror. The whole idea of antimatter, it sounds like something straight out of Star Trek, but it is 100% real.
It really is. It's like for every single particle of matter that we know and love, there's this perfect mirror image of it, but with some of its most important properties just flipped. And the Anti-L-Baryon, it's one of the most interesting characters living in that mirror world.
The symmetry is it's beautiful, really. Every particle has an antimatter twin. So for the electron, you have the positron. For the proton, you have the antiproton.
And they have the exact same mass. The only difference is their electric charge is completely reversed. And look, this isn't just some cool theory someone dreamed up. It's what has to happen when you combine quantum mechanics with special relativity. It's like the universe itself demands that antimatter exists.
Okay, so to really get a grip on the anti-lambda baryon, we kind of have to meet its family on the regular matter side of the mirror first.
Exactly. Which brings us to our second section, the baryon family tree. We're talking about the things that make up almost everything you can see and touch.
And the whole story really starts with quarks. These things are truly fundamental. As far as we know, you just can't break them down any further. They come in 6 different flavors, with great names like up, down, strange, and charm. And here's the thing, they almost never, ever exist alone. They're always teaming up to build bigger particles.
And when 3 of those quarks binds together, what you get is a baryon. Now, the most famous baryons in the world are protons and neutrons, the guys inside every single atom. They are quite literally the bedrock of our entire visible universe. So let's look at the family lineup. A proton is 2 up quarks and 1 down quark, which gives it that familiar positive charge. A neutron is 1 up and 2 downs, making it neutral.
But then you get this other character, the lambda baryon. What it does is it swaps one of its down quarks for a strange quark. Now, this simple swap makes it heavier, way less stable, and it gives it a quantum property that physicists with a bit of a sense of humor actually call strangeness.
Okay, so now that we know the family, we can finally get a proper introduction to our star particle. It's time. Section 3, the anatomy of the anti-lambda. We are officially stepping through the looking glass. And here it is, side by side. On the left, you've got the regular lambda baryon, built from quarks, and on the right, our anti-lambda, built from antiquarks. You can see how every property is just perfectly inverted.
Right, so its baryon number, which you can think of as just a way to count baryons, is -1, and its strangeness is +1. It is a perfect bizarro world reflection of its matter twin.
But here's the catch. Being a perfect reflection doesn't mean it hangs around for long. The average lifetime of an anti-lambda is just 260 picoseconds.
That's just an impossibly small fraction of a second. It pops into existence for this fleeting tiny moment and then it's gone. That makes it so hard to study, but it's also the key to how we even find it in the first place.
And this is how they do it. The anti-lambda decays through what's called the weak force. And when that happens, it almost always transforms into 2 very specific particles, an antiproton and a positive pion.
And that exact 2-particle signature is everything. It's like finding a fingerprint at a crime scene. When physicists see that specific decay, they know without a doubt they've just seen the ghost of an anti-lambda baryon passing through.
Which, of course, brings up a really important question. If these things are so incredibly rare, and they live for practically no time at all, where on Earth do we get them?
Well, we don't get them. We have to make them. Welcome to Section 4, Forged in Star Machines.
Yeah, you're not just gonna stumble across these particles out in nature. You have to forge them in these cauldrons of extreme energy. At places like CERN's Large Hadron Collider, scientists are literally smashing particles together at almost the speed of light.
And the raw energy from those collisions, thanks to Einstein's famous E=mc², actually transforms into new mass, creating this whole shower of new matter and antimatter particles. And somewhere in all that chaos, a few of them manage to assemble into our Antilambda.
And in the absolute most violent collisions, scientists create something truly extraordinary, a quark-gluon plasma. You should think of it as this super hot, incredibly dense soup, where quarks are momentarily ripped free from their homes inside protons and neutrons.
For just a fraction of a second, it's like we're rewinding the clock and recreating the conditions of the universe just moments after the Big Bang itself. And it's inside this primordial soup that anti-lambda baryons are born, not one by one, but in huge numbers.
Okay, so we've established we can actually make them. But why? Why go through all this incredible trouble?
And this is where it gets really good. This is the payoff. Section 5, the quantum frontier. This is where this abstract little particle starts to connect to our actual future.
Seriously, though, what is the use of such a short-lived, exotic piece of antimatter? It feels so abstract, so removed from our daily lives.
But it turns out this particle is becoming a surprisingly powerful tool. It's helping us poke and prod at some of the deepest mysteries in both physics and even technology.
Okay, so there are a few huge reasons why this matters. First, by precisely comparing the anti-lambda to its matter twin, we can test one of the most fundamental symmetries of the universe. If there is even the tiniest difference between them, it could completely upend our current understanding of physics.
Second, it gives us clues about one of the biggest questions out there. Why is our universe made of matter? What happened to all the antimatter that should have been created in the Big Bang?
And then there's the really futuristic part. The complex way its 3 antiquarks spin and arrange themselves could, in theory, be used to create a totally new kind of qubit, which is the fundamental building block of a quantum computer. It's a long shot for sure, but an absolutely fascinating one. And all of this leads us to our final, really big picture section. An antimatter future?
Right. And this is where we have to be both visionaries and also really realistic, because the potential here is just massive. But so are the challenges.
And this really is the great paradox of antimatter. The potential is honestly mind-boggling. Matter-antimatter annihilation is by far the most efficient energy source that is theoretically possible. It could literally change everything about our world.
But the challenges are equally immense. It's incredibly unstable, it's ridiculously expensive to produce even tiny amounts of it, and oh yeah, it annihilates the second it touches anything made of normal matter. I mean, just figuring out how to store it is a monumental problem we haven't solved.
But that vision is what drives all this research. And as Jörg O. Schneeppert puts it so well in his essay, the ultimate goal here is to go from just observing these particles
to learning how to actively control them. If we can ever make that leap, it could truly pave the way for a whole new era of quantum technologies we can barely even imagine right now.
And so that really leaves us with a big question, doesn't it? Is this amazing little particle destined to just remain a beautiful scientific curiosity, a tiny window into the fundamental rules of our universe?
Or can we actually learn to harness its strange and powerful properties and turn it into a real building block for our future? Right now, we don't know. The answer is being written right now in labs all around the world.
We want to give a huge thank you again to Jörg O. Schneeppert. His work was the foundation for this entire deep dive. For a much closer look at this and other quantum topics, you should definitely visit his site at schneeppert.de.
Thanks so much for joining us on this deep dive. We'll see you next time.
Schneeppert.de is a private project by Jörg O. Schneeppert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.